Recording is rolling. It is Monday, September 29th. So I have this teacher of the year ballot. So we're going to go through this, teach you guys some about ranked choice voting. And then we're going to take the rest of the class to solve a bunch of puzzles. Right, so they're going to look like this. Because I'm looking through your guys' upcoming AP classroom questions. Now, AP classroom is not due for a couple of weeks because there's a bunch of rotational and typical four type questions on there that we haven't even covered yet. But I did see a center mass question, so I want to cover that with you guys. I want to go back and make sure that you guys can do if I turn the sport bottle into a train, like choo choo, or can you solve this tension and links to solve one of this? Ooh, a ball bouncing off the wall. I want to do with you guys, and then we'll go back and we'll do some more examples with. You guys should be able to do Atwood, but you guys will show me later. Can you solve that? Okay. And then my first period class, we were also able to solve this by the end of class. Okay. And then, well, probably not the inclined so much, but here. So some of this is a little bit new. Some of these are some review. We'll be doing those later this week. I have some labs and activities lined up for you later this week for AP of pulling up our key for you guys, so you guys get more exposure to that. You guys remember your chapter puzzles are due Friday, right? You guys remember these chapter 4 or 5 puzzles? Back last Friday, I narrowed it down to 10. I was recommending to you guys because those are also, and then I'll get you guys a quiz by Friday. So you guys go with the agenda, what we're doing. All right, so let's go back to the top here. So every year, teachers get one of these ballots. Now, one's for employee of the year. We're not going to look at that, but we'll look at teacher of the year here. And so I always ask my students who would be the best candidate for teacher of the year out of the options they give. So here we got Miss Barnhill, Mr. Owens, Miss Wayne, and Miss Berman, because I haven't had any of these teachers, but you guys have. Right. And this is also a really good opportunity to learn a little bit about voting systems. Now, there are lots of different voting systems and different ways to calculate votes and for different methods, whatnot. Right? But here, I mostly want to contrast what is ranked choice voting versus something called first past the post. Right? And then within ranked choice, there's different ways to calculate it. So we'll do a process called instant runoff. Right? Now, on your guys' end, I just want you guys to either think in your mind, or if it helps you to jot this down on paper, who's your first option out of these four? Like, who would you really want to win out of these four? Right? And then, do you have a second choice and maybe even a third choice? So, for example, suppose you really like Miss Barnhill and that would be your number one choice. Right? And then after that, okay, well, maybe I like Miss Wayne second, and maybe you haven't even had the other teacher, so you just stop ranking. Right? So, like, there's my number one, my number two, and then I'm done. Right? Or, hey, maybe you like Mr. Owens as your third choice. Right? So you can rank it as few or as many as you want. You guys get the idea? Right? Right. And then what I'm going to do is go, well, okay, if we did this officially, you guys would do this on paper and I would tally all the votes up. But we're going to do a quick method. And the quick method is I'll say who is voting for as their number one choice for each one of these four. Right. Okay. Now, suppose here, just a side thought, what if you really like Miss Barnhill? It's like, oh man, I really want to vote her number one. But I think you're probably only be like one or two as, and I don't know if she's going to be popular. So maybe I'd have to do some strategic voting and vote for someone who else who might have a chance of winning. Right? Guys, don't worry about that because we're going to do a ranked choice instant runoff method, in which case there's no such thing as like wasting your vote. You don't have to worry about strategic voting, anything like that. Here, you guys will see if it plays out. Right? All you guys have to worry about right now is who is your number one vote. Okay? All right, you guys have that? You guys have somebody in mind? Yeah. Somebody in mind for your number one vote? Right, you guys ready? Yeah. All right, so let's see, show of hands. Who is voting for Miss Barnhill as their number one? Barnhill number one. Barnhill number one. Got one, two. Okay, I'm counting two there. Okay, who's voting for Mr. Owens for number one? We got 1, 2, 3, 4, 5, 6, 7, 8. 8? Okay, I think 8 there. All right, who's voting for Miss Wayne, number one? Miss Wayne got 1, 2, 3, 4, 5. Okay, count 5. Who's voting for Miss Berman, number one? Got 1, 2, 3, 4, 5. 6. 6. Count 6. Right. Right. So it comes out like that. Okay. This is a pretty good set of numbers for the demonstration I'm going to do with you guys. Right. So that's who everybody like as their favorites. Looks like that, right? Like that. Now, at least systems here, really, it's kind of two systems because instant runoff is a way to count ranked choice. So really, this is sort of the same thing. Sorry, just not quite a little bit. And first past the post is a different method. Guys, suppose you turn 18 and you go vote in like an official election, like in the state of Florida. Right? The state of Florida, most states in those states actually use which method to count the winner. Yeah, it's first past the post, right? And what does that mean in this case? Like, suppose this the numbers came out like this: is who would be winning the race according to first past the post? Mr. Owens, and actually he would win. That's it. First past the post, you just vote for one candidate, and then you walk out, and that's the end of it. Whoever gets the most votes wins. Okay? But you guys can probably see, a downside to that type of system, which is like, what if everybody who didn't vote Owens there first? What if they all collectively like somebody else better than Owens? Right? Like, what if we congregate behind Miss Berman, for example? Right? And I don't know yet, but we can find out. Right? See, there's no true majority. You guys see that? First past the post, you don't actually need a majority to win. You just need a. Guys, what if you don't have the majority, but you have the most votes? What's that called? Starts with a P. Plurality. Okay. So Mr. Owens here has a plurality, but nobody has the majority. Okay? So what we'll do is you strike the lowest number of first place, which in this case would be Barnhill. Okay? And then behind the scenes, what the machinery does is it retabulates the votes. So okay, well, who is Miss Barnhill voters like second place vote? And then it recaps the votes. Now, just to move things along a little bit, here's what I'm going to just save a little time, right? Is we're going to fast forward a couple of iterations, and suppose it narrows down to these two right here. Okay, can you guys imagine that? Let's say it eventually narrows down to just either Owens or Berman. Okay, you guys ready to vote again? So you're only voting on either Owens or Berman. You guys got it? Okay. All right. So who wants Mr. Owens as their number? Well, is the favorite of those two. Mr. Owens. Who's voted for Mr. Owens? Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 on Owens. Okay. And who's voting for Miss Berman? Miss Berman. We got 1, 2, 3, 4, 5, 6, 7, 7. All right, there you go. All right. So that's how it pans out. All right, so now there is a true majority because it looks like at least 18 of you guys voting. Okay, now there actually is a true majority. Okay. Now, so where's my earlier classes? Because I'll mark you guys down as fourth period. All right, so this is fourth period. So I'm doing this for all my classes today. And at the end of the day, I'll figure out this stuff. Okay. Now, my first period, interestingly, it worked out like this: is Mr. Owens had the lead after one iteration, or you say you would have won for past the post, right? But when we went to the second iteration, actually Miss Wing came out ahead there. So that was an earlier class. I did this for all my classes. All right, so there you go. There's first past the post versus ranked choice. Okay. All right, so let's hit some puzzles here. Hit some puzzles. Right, now the center of maths. So every physics textbook has this in a different chapter, so it's kind of weird, but this will show up on an upcoming AP classroom. So really, to find the center math point, all you do is get a weighted average. Here, can you guys read this equation? Here's what is this symbol right here? Yeah, sigma, summa, or summation. You're adding up all the mass times location, and then you're dividing by the sum of the masses. And that gives you, effectively, the average location. So, as an example, what if you have two masses? Maybe they're connected by a stick. Can you guys imagine like a real skinny dowel here, like a stick, right? Which maybe is tiny mouse by comparison. Okay. Like, where could it balance on your finger? Could it balance, maybe, wouldn't it be closer to the large one? It could balance on your finger. That's one way to find the center mass. I'll probably do an activity eventually with you guys about that. Or what it does, what if you took that whole system, again, like stuck on a stick, and you threw it through the air, and it starts tumbling, like tumbling like this. Guess which point it would spin about? The center mass, right? And so here's how this plays out for two masses. So mass times location for object A plus mass times location for object B, divided by sum of masses. There's your center mass. That's okay, right? Now, do you guys see this is actually all along the x-axis, though? Along the x-axis? Right. What if you had a two-dimensional situation, which you guys are going to see on your AP classroom questions? Okay, so let's do an example for center mass. Okay, center of mass. Okay, so I'm just going to make something up here. Okay, let's do like this. Okay. What if you have an x-axis, but you also have a y-axis? Interesting. So this, throw on some coordinates. Okay. And let's do this for, how about three masses? So maybe I'll put one mass right here. I'll put one mass right here. I'll put one mass, how about down here? Like that. Okay. I need to assign them some values. Right? Maybe these are like, could you be that these are all like a giant foam board, like they're all glued to a foam board? maybe they're really, really heavy compared to the foam board, so the foam board doesn't really matter as much. Maybe it's negligible itself, right? But these three masses, all right, let's call it, all right, let's do this. Let's do random number generator getting 72. So let's have this guy as 72 kilograms. Ooh. All right, what's we got? 11 kilograms. And 28. So this guy could be 28 kilograms. Okay, so those are the masses. Okay, you guys got that? Okay. Now, here, I'll make the heavier ones larger. So this might be like really, really big mass right here. Okay, that one's the smallest one, so I'll just leave it alone. But this one looks about 2 or 3 times as big, so maybe it's not about like that. Okay. Yeah, right. Okay. All right. Now, again, if these three masses are glued to a giant massless foam board, right, and you wanted to balance that on your finger, could you guys kind of guess where the center mass would be about? Where could it balance on your finger? Probably, do you guys think maybe about here-ish, somewhere about?
Yeah.
Okay, I'm going to make a guess. I'm going to guess it's sort of close to the y-axis on one side or the other. Maybe actually, let's see. 3 times. Well, probably somewhere fairly close to the y-axis. It's kind of hard to tell if it's on the right side or the left side. Okay, but also probably pretty close to here. I'm gonna make an X. That's my guess. That's my guess. Probably pretty close to that point. Okay. And the way we can find out exactly is we'll do this method for both the x-axis and also the y-axis, and then we'll have a coordinate. You guys get that? Okay. So for x bar, say like the average x value, let's do mass times location for each one of these three. So the 72 kilograms times, and could this be at -2 location? Okay. Maybe could this be in meters? And this could be also in meters. So -2 meters plus, and then here I have 11 kilograms at the 1 meter. And then I have plus 28 kilograms at 3 meters. Right? Isn't that all the mass times location added up? Okay. Divided by the sum of the masses, that would be 72 plus 11 plus 28 kilograms. Right? And that be true? Right? And that'll give me the average x location. Right? So the average along the x-axis. So let's do 72 times -2 plus 11 times 1 plus 28 times 3, all collectively divided by 72 plus 11 plus 28 kilograms. Okay. Right, so do you guys see that the kilograms are going to cancel? That'll leave me with meters. So I'm getting -0.44 meters. Okay. Hey guys, the fact that it's negative tells me, yeah, it is to the left of the y-axis. Okay, so actually it's kind of back here. So I wasn't too far off, right? Off by 0.44 meters. So it's somewhere just to the left of the y-axis. Okay, but what about how far above the x-axis? Right? What's the y-coordinate of the center mass? Right? We did a similar process for a y bar. So take the 72 kilograms times, now in the y direction, this is like 1 meter up. About 1 meter. Right, plus 11 kilograms at, isn't this 4 meters up? 4 meters up. Stick 4 up here. Okay. Plus, and then I have 28 kilograms. Now this one's sitting on the x-axis. So guys, what is its y value? 0. Yeah. 0 meters. 0 meters up. Okay. So add all that up, then divide by, again, 72 plus 11 plus 28 kilograms. Okay, do you guys see that? Okay. All right, so y bar, the average y value would be, okay. Now, ahead of time, I was guessing it would be right about here, but we're going to see for sure. Okay. So what's 72 times 1 plus 11 times 4 plus 28 times 0, all collectively divided by 72, 11, 28. I'm getting 1.05 meters. Yeah. So let me mark that point exactly. So that's -0.44 is right about here. 1.05 is like right here. Okay. There's the actual center mass. Okay, I just marked it right there. Yeah, so my guess is probably right there, but the actual value numerically came out to pretty close to that. It's right here. That is the center of mass. So I'll say center of mass is at the coordinate negative 0.44 meters, and then 1.05 meters. That's the answer. You guys got that? All right, so give the center mass of them. All right, next. Who's next here? Train gang. So we're gonna start from this chain gang idea. You guys remember doing this mini lab? You had spring scales and weights like this, and the top spring scale had to hold all the weight beneath it. But by the time you got to the bottom spring scale, it only had to hold the one weight beneath it, which was not as much force. Isn't that? Okay. So we're just gonna take that story and turn it horizontal and turn it into a train. Okay. So here's the question: is what are the tensions and the train links? Wait. Okay. Here, let's draw this up. So let's get a train. Got little train wheels on it. Okay. And then let's have some box cars. Box car, box car, box car. And these are all connected by links. Okay. Making the links pretty big just to make them apparent they're definitely there. Okay. And then maybe I'll call this tension A, call this tension B, and tension C. Okay. I need to throw in some masses. So let's go about 1,000 kilograms here. Let's go 3,000 kilograms here. We'll call this 5,000 kilograms. Thanks. Thanks. You guys got those? Right. And then the engine, it doesn't matter. We'll say the engine's powering it. It doesn't matter what the engine is. Right? It's just pulling everything behind it. No, here, side question here. Because I haven't actually given you enough information to solve this. Right. But what about this? Is what if this whole train system is going at constant velocity? Yes, if the whole system's moving at constant velocity, constant velocity, then what would be the tensions in those links? Zero. Yeah, zero. Zero. There'd be no tension at all. Right. This whole system would just be rolling from inertia or momentum. Yeah, you don't need to be pulling at all. Because if you provide a pulling force, that doesn't cause constant velocity. That causes what? Acceleration. Yeah, an acceleration. Yes. Okay. So I do need to tell you an acceleration. So I'll say given acceleration equals how about 3 meters per second squared? Okay. So this engine is pulling. Maybe there's a friction between the wheels and the track. It's pulling. Right. So this whole thing is accelerating forward at acceleration equals 3 meters per second squared. Okay. All right. Hey guys, if you know these masses and you're also told the acceleration and you're asked for a tension force, what formula do you need to plug this all into? Newton's second law. Newton's second law. Right. Isn't this a job for Newton's second law of motion? Right? Which goes like this. Net force equals mass times acceleration. That's one way to think of it. Okay? I mean, you have the masses, you have the accelerations, we can find the net force. So tension A. Ooh. Doesn't this tension A have to pull all these parts behind it?
Yes.
Yeah. So, and we'll say these are on like frictionless wheels. So that'd be the sum of the masses, and that'd be like 5,000 kg plus 3,000 kg plus 1,000 kg, accelerating at 3 meters per second squared. So let's see, 5, 6, 7, 8, 9. So 9,000 times 3. That'd be 27,000 newtons. Could you also call that 27 kilonewtons? Same thing.
Yeah.
Right, how about tension B? Now, this link only has to pull these two parts behind it. So that'd be 3,000 kilograms plus 1,000 kilograms. Also accelerating at the same acceleration, because they're all accelerating the same. Okay, so 4 times 3, that'd be 12,000 newtons, or 12 kilonewtons. Right? Okay. And then this last link that's just pulling the caboose back here, that's all it has to pull. It's just 1,000 kilograms. It has to make it accelerate at 3 meters per second squared. So that's 3,000 newtons, or if you like, 3 kilonewtons. Okay. Right, so you guys solve train links. You guys do that? Same thing as the chain gang, just turn sideways. All right. What's next on the list? Are you guys ready for the next one? Okay, so we're moving on to bounce a ball off a wall. Bounce a ball off a wall. Now my poster version shows a two-dimensional version of this, but I'm just gonna simplify this to one dimension and then we'll work from there. Okay, so this so let's see, what is the force from the wall on the ball? Okay. Let's look at a top view. Top view. So looking straight down. Okay. I'm seeing this wall right here. I got this wall. And let's have this ball. It's coming in at some velocity. Okay. Some initial velocity. And then it bam hits the wall. Okay. And then it rebounds at some different velocity. Okay. Let's say it's basically headed straight towards the wall, and then it rebounds straight away from the wall. Okay. It's straight towards and straight away. Okay. Okay, so I'll call this like V final. Okay. Okay, so now if you're interested in the force from the wall on the ball, okay, that would be where the ball is making contact with the wall, right here. Okay. Because which direction do you draw that force? From the wall on the ball? Would it be straight away? Like that? Okay. And what kind of force is that? Normal force, it sure is. That would be a normal force, wouldn't it? Right, from the wall and ball, the boing. Okay. Actually, you know, while the ball is colliding with the wall, which force is bigger? The force from the wall on the ball, or the force from the ball on the wall?
On the wall.
Equal. Is that equal? Oh yeah, winner. Yeah. Is that a Newton's third law question? Okay. AP always likes to slip a Newton's third law somewhere. We're at least expecting it. Yeah. Guys, they're the same force. The force from the wall on the ball is the force from the ball on the wall. Well, same magnitude, opposite directions. Right? One's left, one's right. Now to solve this though, you need some numbers. So let's make this a baseball. Let's call it 0.45 kilograms. How fast do I throw this ball? Let's go 9 meters per second. 9.0 meters per second. Okay. You guys, what's the fastest, if the ball is stationary, what's the fastest it could possibly rebound away from the wall? Yeah, it could be 9, right? Okay. That's if it's what's called perfectly elastic, okay, which is kind of like my Newton's crater right here. Okay. You guys think this right here also models perfectly elastic? Or pretty close, right? Okay. But and it could be less than that. Let's say this is to the left, and let's say it rebounds at 7.0 meters per second to the right. Okay, so like a little slower. That's more realistic, right? And there's one more detail you have to know to solve this. You have to know the time interval of this collision because that matters too. Okay, like if this is like a bounce ball, say boy, right? You don't actually need as much force to make it reverse. But if it's like a hard little pellet ball, it's like pow, right? Then the force would actually be bigger to produce this exact same set of numbers. So let's say the time interval of that collision is 0.05 seconds. Okay. I think that could be realistic, right? A fraction of a second, something like that. Okay. All right, you guys good? Right. So let's see. The question is, what's the force? I told you the mass in question. I told you something about velocities, that you can find a change in velocity. And I told you the time interval this all happens in. So big picture here. What's one formula you're going to need to solve this? Kinematic. Okay, kinematic. There's a kinematic half of the story. Okay. Because if there's a velocity change in some time interval, is there an associated acceleration? Right. And after you have that, so something about this guy right here, right? Right. After you solve the acceleration and you have mass and you want force, you also need to apply what? Yeah, F equals ma. Newton's second law. Right. If I just jump straight to that, I go like F equals ma. Right? Maybe it's this normal force right here. It could also be the net force. That's why this is a top view, because we're not considering the weight of the ball, right? Just the mass. Okay, so the normal force in this case would be the mass of the let me let's do this. All right. So the mass of the ball could be 0.45, that's kilograms. Okay. Now acceleration. If you take this kinematic formula that you guys were recommending and rearrange itself for acceleration, wouldn't that be change in velocity over time interval? Wasn't that actually the initial definition of acceleration? Rate change of velocity? Rate change of velocity? Okay. I'll put that right here. So change of velocity over change in time. And I know the time interval is 0.05 seconds. Okay. But what about the change of velocity? What is the change of velocity of the ball? And don't say 2. Nine to the left, 7 to the right. What's the difference?
16.
16. 16. It's a completely reverse direction. Right? So isn't it like this? We end up at 7 meters per second. Subtract negative 9 meters per second. Right? Don't you have to subtract a negative? Right? So I'm subtracting because there's a difference, and this is negative because it's the opposite direction. It's left versus right. Subtracting negative. Guys, the change of velocity is 16 meters per second. Sure. How about this? What if it did rebound perfectly elastically at 9? What's the difference between 9 to the left and 9 to the right? That would be 18. Right? And if you messed up and forgot that and said, "Oh, it's 0," guys, wouldn't 0 change of velocity? It means the ball just keeps on going. That wouldn't make any sense. Right? Yeah. Right.
How did you rearrange the kinematic equation?
Yeah, here, I'll do that too. So we started with final velocity equals initial velocity plus AT.
Yeah.
Right? If I'm solving for this A, I can subtract over the V naught, so VF minus V naught, then divide down to T. That's equal to A. And that fits in right there, or if you like, right there. Okay. So change of velocity over time interval. Okay. All right. So what do we got here? We got 0.45 kilograms ball times we have 16 meters per second change, and this all happens in 0.05 seconds. Okay. What's 0.45 times 0.05? I'm looking at 144 is the number on my screen. This is a normal force. Guys, is that all 144? What is that? 144 what? Newtons. Because we're talking about a force. Kilogram meter per second squared. That's newtons, isn't it? Yeah, that's the force right there. That's it. Okay, guys good? Good. Okay. All right, so that's remember that's if you throw the ball straight at the wall and it rebounds the other way. Okay. Now my poster version. You guys ready for the poster version? It's a little more complex. Okay. Well, I have a blue banner because this was in the momentum section when you have collisions like that. So you'll definitely see this come back later in the year. Right? I did make this perfectly elastic. Did you guys see whatever speed I threw the ball? It could leave at the same speed. Right? No, if that's true, that's perfectly bouncy. Right? So a little simplification. Right? This is also in 2 dimensions, so it's still a top view. We're still looking down. Right? Right. Now you have to consider forces in both the x and the y direction. But in the direction that's parallel to the wall. In the direction parallel to the wall, did the ball ever change its motion parallel to the wall?
No.
No. It was moving this direction, and post collision, it's still moving that direction, same speed, same angle. Yeah, it never did anything there. Also, what goes hand in hand with that? Do you guys see the word frictionless? Okay? Because if there was friction, maybe it would sort of slow down the ball a little bit. Right? But that didn't happen here. It's a frictionless ball. The ball is frictionless. It's elastic. Okay, so in this direction, there actually is no force. All the force is the one that's labeled here, which is the normal force of the ball, which is kind of what we just did, isn't it? Okay. So really, even though this was in 2 dimensions, I simplified this enough that you can make it look a lot like what you just wrote in your notes. You just have to take a sine component of this velocity. Okay? Do you guys see that whatever this velocity is times sine of this reference angle would tell you how fast the ball is headed straight towards the wall? Is that right? And if it is elastic and frictionless, then wouldn't these 2 components be the same thing? Right? So put it all together. It's the same thing we just did. It's basically the second law of motion. Okay. And then this is where this 2 comes from. Because if it's elastic and frictionless, then this component is equal to this component, hence the 2. Is that so 2 sine theta? Right. No, it's very special to this very simplified case. Okay. All right. Guys good? All right. All right, what do we got next on the list? Next on the list. All right. You guys ready to do some Atwood practice? Atwood. All right, you guys remember this Atwood right here? We'll do a classic Atwood. Okay. So there's a lot of questions you can ask about Atwoods, but the 2 classic questions you usually get are what is the acceleration of the system? Or how it's usually worded is, what's the downward acceleration of the large mass? Or something like that. And also a good follow-up question is, what is the tension in the connecting string? Connecting string. Or rope, it's not string or rope, whatever, right? Where the string or the rope itself has negligible mass compared to the 2 weights, right? All right, so let's get a classic Atwood right here. Classic Atwood. So I got my pulley, maybe it's like anchored into the ceiling, or maybe you're holding it at rest, right? Okay. So like a massless frictionless pulley. This guy right here. Massless frictionless pulley. Okay. And let's get a couple of blocks on this connecting rope. So start with some mass here and some mass here, right? So I'll start with the heavy one on top and the small one on the bottom, so that when I let it go, it starts to rest. Like that. Okay. All right. I need some masses. Let's come up with some masses. Magic ball. 96. 96. I guess this guy's 96 kilograms. That's a heavy one. And what's my smaller block? 49. Oh, yeah. So this guy is 49 kilograms. Okay, so we got 96 versus 49 kilograms. That's actually really close to a 2-to-1 ratio. So you know what? I bet if you change this to 2 kilograms and this to 1 kilogram, it would be almost exactly the same acceleration. Now the tension, of course, would be wildly different. Okay, but just get the idea. Like if you know the ratios of these masses, then there's some acceleration based on that sort of thing. All right. So let's do free body diagram here. Let's see what these weight here. Because what is this one weigh right here? What's this weight? Yeah, 960 Newton. Oh, so we're gonna call G equals 10 meters per second squared. Okay. And then what does this guy right here weigh? Yeah, look at that, 490 newtons. Right? If you added more to this free body diagram, well, eventually we're gonna have to answer the question: what's the tension in the connecting rope? Okay. So would there be a tension that's smaller than 960 newtons, but also larger than 490 newtons? Okay. And it should also be the same tension on both. So this same tension, isn't it? Well, it's about F sub T. Right. Right. Now there's 2 main methods to solve this set of questions. One method is you could set up a system of equations for these 2 blocks. You could focus on this block and focus on this block, which is basically these 2 green boxes down here. And then you don't know either the tension or the acceleration, but 2 equations, 2 unknowns, you can solve it. But what I'm going to do with you guys is my favorite method is called a whole system approach. In the whole system approach, you have Newton's second law of motion. So A equals F over M. Okay? And this F, this net force, I'm going to treat this like a tug of war on this 2-block system. So I'm not looking at each individual block. I'm looking at the 2-block system. Do you guys see that?
Yeah.
Now, I cannot right away figure out what the tension is, but I can save that question for later. I can very quickly figure out what the acceleration is. So we're doing a whole system approach. You guys get with that? Okay, so whole system approach. Approach. Okay. From this point of view, the acceleration of the whole system would be difference in force over sum of mass. Okay? So guys, what's the difference in forces? 960 minus 490. That many newtons? Is that true? All right. Is this 960 newtons says, let's go clockwise. This 490 newtons says, no. Let's go counterclockwise. And they fight each other. You see it? Okay, now, of course, the big guy's going to win, so this whole thing goes clockwise. But how much mass is being moved around? Yeah. 96 kilograms plus 49 kilograms. It has to move all that inertia. So this net force in the numerator has to move all this inertia in the denominator. Is that it? And that's how you get the entire acceleration. One way to get it. So 960 minus 490 all divided by, and then in parentheses 96 plus 49. That would be 3.24 meters per second squared. Just like that.
Yes,
Why is it meter that precise one's great? Oh, just because that's acceleration.
It's an acceleration. Yeah. Also, newtons per kilograms gives you the same unit, meter per second squared. Oh. Here's what I thought. Remember, if this was 2 versus 1 kilograms, it should be approximately the same acceleration. Let me see 2 and 1. So if I do 20 minus 10 all over 2 plus 1, it gives me 3.333. Yeah. Because I was saying the ratios of the masses are very similar to 2 to 1 ratio. So the 2 to 1 ratio has almost the same acceleration. Okay, so a little side thought there. All right. So now that we have the acceleration, this is the downward acceleration of the large block. It's also the upward acceleration of the small block. It's the same thing. They're tied together. Okay. Now we can go get the tension in the string by focusing on either this block or this block. Okay? So we can set up one equation or the other. You don't have to do both in this case. Right? How about I'm going to focus on the small block right here. Let's do this one. So from the point of view of just the small block, I can set up another F equals ma. I could say F net equals mass times acceleration just for the small block. Thank you. And in this case, the net force would be what? How do you write the net force?
Normal force.
Yeah, the tension pulls up. The 490 Newton weight pulls down. Right? Wouldn't that be the net force on that block? One up, one down. And that results in how much mass moving? Just the 49 kilograms, because we're only focused on that block. And how much does it accelerate?
3.2.
Aha! That's right there. 3.24 meters per second squared. That's it. Okay. So, see, multiply that, add over 490, see what we're going to get here. It's 49 times 3.24, then add over 490. So I'm getting the tension force is 649 newtons. There you go. That's the tension in the connecting rope. Okay, guys good? Okay. Let me do something else with this. Let me take this tension. Okay, guys. Isn't that also this tension as it applies to the other block? Right? I bet if I do Newton's second law of motion plugging in this now known tension, I should confirm that acceleration. True? Okay, let's try that out. I'll just do this on my calculator screen. So I'll take the net force on this other block, this heavy block, 960 newtons down, subtract off the 649, pulling back the other way. There's the net force on this block, right? The difference. Then divide that net force by its own mass, 96 kilograms. Now guys, see if you guys are following. When I hit enter, I better get a number that's really, really, really close to what? 3.24. Right, because we found that before. This is for the whole system. So better also apply that in an individual block. There it is, 3.24. It's the same thing. Except, same thing. So it worked.
Why don't you have to calculate like the tension on the other?
Yeah, you could have done that too. Okay, could have.
It's the same tension, so you can choose.
Yeah, it's the same tension. So what I wrote on paper is I just did it from the point of view of the small block. I could have set up an equation. Right. Okay. And then in my calculator, here I'll scroll up. Okay. I went and double checked on the large block because in my calculator screen right now, this is the large block. Right. And then it also came out to the same acceleration. So it worked out. Yeah. The same tension on both blocks. Okay. Right. So some classic follow-up questions. You can go kinematic with this. You could say, how far does this move in some time interval? You say, how fast after some time interval? You could say, how fast does it move after some distance moves? Right. Can those all be kinematic? Okay. And then I think your textbook also had the question, what's the tension in this other string connecting this to the ceiling? And that just ended up being 2 times the tension force, didn't it? You guys remember that? Okay. So this tension times 2 is the tension up here, right? Okay. Okay, so we're good with that wood. So next on my list is equilibrium. So we've of course done this before, but I just wanted to do some more practice with you guys. We're basically gonna do this again. Right, you guys remember this? Remember this? Right, so we'll do a practice run through. Practice run through. Okay. Right, so the question is gonna be, what is each tension force? So what is each tension? Right. So let's set up a Cartesian grid because I know this is going to go Cartesian at some point. So Cartesian grid right here.
Yeah.
Right. We got a x-axis, we got a y-axis, xy. Right. Let's have three ropes come together and they all connect right at that center dot. Right. So right at the origin point of the Cartesian system is where all these three ropes are going to connect. So I'll have one force straight down. This will be some weight, some mg, some weight. And then let's have a couple of tensions on some angles. So let's have one going this way, and then one kind of going about sort of like this. Okay. Okay. I'll call this tension left. I'll call this tension right. Okay. Right, so that's a great case setup. Now, right. The example I did with you guys back the other day in your notes, I gave you alpha and beta with respect to the horizontal in that Masterman poster. I'm going to change things up a little bit, just so you see something a little different. I give you angles, not relative to the horizontal, but relative to the vertical. You guys see that's different? Right? So just keep you guys on your toes a little bit. Right? And I'll make nice numbers though. Let's call this 37 degrees. Let's call this 53 degrees. Okay. Guys, why did I pick 37 and 53? Because I'm setting up what triangles?
3, 4, 5.
Yeah, 3, 4, 5 geometry, which is special. Yeah, 3, 4, 5. Okay, but you can't solve any of this without knowing what the weight is. So let's figure out what weight are we talking about. 20. It's 20 newtons. 20 newtons now. Sure is. 20 newtons. Okay, you guys get that? 20 newton weight. Okay. All right, now let's go split these tensions into. I should have asked you guys, what do you do next?
Make them into right triangles.
Yeah, components, right triangles. Yeah. So components. Yeah, I like the right triangle method myself. Draw a right triangle method. So how much left and how much up? And how much right and how much up? The little arrowheads. Okay. Guys, notice I dashed those components. So I'm not sort of like double counting them. Okay. There are really only three vectors, right? One weight and two tensions. Okay. Right. So by dashing them, specifying those components. Okay. Okay. Ooh, guys, what is this angle up here? 37 degrees. And what is this angle right here? 53 degrees. Okay. If you wanted to, could you play with this angle here? What is this angle here? This is 53 because it's complementary to 37. I just made it complementary to each other. Okay. And the salt is 37. All right, so you can play all those. That's fine too. Now, I don't know what the tensions are, but I do know what the components are in terms of those tensions. Okay. So this right here, could this be tension left, whatever that is, times what? Yeah, sine 37, like that. Okay. And sine of 37, isn't that like 3 over 5? So this could be, I've been doing fractions today, so I'll just use fractions. I think the other example you have in your notes from a few days back, I gave long decimals with like 3 or 4 digits of decimals, but let's do fractions today because that'd be fun. Okay. And let's do all the rest of these. So I think this one right here could be TL times cosine of 37 degrees. This one right here could be TR, as in the right tension, times sine of 53 degrees. And this one right here could be TR times cosine of 53 degrees. Okay. Then in black ink, I'll go write the fraction form of all those. Cosine 37 is a quark this, so quark this of TL right here. We got sine 53, that's a quark this of TR. And this is 3/5 of TR. And this is 20 newtons. Right, so I circled the 5 either forces or components that you need to use for set equations. Yeah.
What's that buffer on the right? Is it this?
Yeah, that's cosine of 53 degrees is 3/5. Yeah, 3/5 times TR. Okay. Alright, so you guys got all those. Okay. Now the two conditions to solve this are like this. The sum of the forces in the x direction goes to 0 newtons. The sum of the forces in the y direction also goes to 0 newtons. Okay. That's gonna set us a system you can use to eventually solve this. So these two right and left have to cancel out. You guys notice I drew my picture like that? Made these the same magnitude, just opposite directions. And then also in the vertical, these two upwards have to cancel out with this downwards. So that's it. Let's go bring this condition right here. Okay, maybe I'll put some space here. So I'm gonna say 3/5 TL, which we don't know. Here. Okay, since that's left, can I call that negative? Is that okay? Negative, great. Plus 4/5 TR. Tension right. Has to go to 0 newtons. Better. Okay. And I can slide this over and say for this TR equals 3/5 TL times both sides by 5. So tension on the right side equals 3/4 of the tension on the left side. Or you could do it the other way. You could say tension left is 4/3 of T right. That's okay too. Right? I still don't know what those are, but I can set up this other expression in the vertical and then do a substitution. You see it? See where this is going? So bring this other guy down. So now let's look in the vertical direction. So in the vertical, I have 4 this tension left plus 3 this tension right minus 20 newtons goes to 0 newtons. Okay? And here's where I can substitute. Right there, right there. Instead of tension right, I can put it in terms of tension left. Now I'll have one expression with one unknown. So 4 this tension left plus 3 this times 3/4 tension left also. Now they're both left. I can slide this over and call it 20 newtons. They add all this up. What is 4/5 plus, that's 9/20, isn't it? It's like 1.25, it's like 5/4. 5/4 tension left equals 20 newtons. Here. Right. Oh, hey, we're gonna get nice numbers. We got a whole number out of this. Guys, can I multiply both sides by 4/5? So therefore, continue down here. Therefore, tension left is 4/5 of that. Is that 16 newtons, I think? Is that right? And then, you guys remember this from before? Well, I remember tension right is 3/4 of tension left. Oh man, this worked out really nice. Watch this. What's 3/4 of 16? 12. Oh man, yes. We have a lucky random number generator right here. Lucky ball. Yeah. Give us full number of answers. Does that look about right? We got 20 newtons down here. And then I found out what these are. I have 16 newtons here and 12 newtons here. Yeah, that's it. This whole thing. And there's the bell. Alright, you guys have a good night. No, stop.